Okay, so good afternoon, everybody, for this first webinar of the week. So we get two more seminars, by the way, one tomorrow at 3 and one on Thursday at 11. And so it's my pleasure to welcome Sam Alperin from Los Alamos National Laboratory. And this time we talk about emergence of classical pattern forming dynamics from quantum models. And I hope you will explain this very nice pictures of Thank you.
Well, first, I had another question since being here, what Los Alamos looks like. I can't show you what it looks like against the rules, but this is what it generally looks like around that area. This is the greater metropolitan area of Los Alamos. Cactuses and juniper. So while I've been here, I've been thinking a little bit about what kind of connects our common theme. So some of us are here because of mutual interest in mathematical methods. Right? I think a lot of us are interested in asymptotic analysis. There are people here interested in Widom theory and IST, things like this. And then there are also in common themes regarding physical systems. We've seen talks on actual physical observational oceanography, right? Talks on quantum gases, nonlinear optics, all of these things. So I think everyone kind of fits generally in here, or here some mix, but really what we're all interested in is how the interplay of transport, which spreads things out quite generically, combines with nonlinear dynamics to get solitons or solitary structures, something which is localized in space and does not spread out. So I think this audience in particular, I don't really have to convince anyone that solitons exist. It's kind of obvious to everyone here. But it's worth thinking about why this is so surprising, right? We saw pictures of, this is not from the laboratory, but we saw people who were here a couple weeks ago in a water tank, a soliton just like this. And it really is special because this wave, while it's moving in space, it's moving ballistically, right? It's not spreading out, even though water is actually made up of a great many objects, right? This is a collective phenomenon. So in many body systems, this is very uncommon in nature. Right? Things tend to disperse, they tend to spread out. In general, nature delocalizes concentration. Right? So here we have a soliton, as we all know, because there's not only this delocalizing transport, but there's also something there. So most of what this talk is going to be about is actually this thing here, really what the nature of this transport is, where it can come from. So first we'll go to what was on the introductory slide, this super cute pufferfish. You see these patterns all over nature, right? Jaguars or cheetahs, I can't remember which. Fish, coral reefs, all over the place, because these are universal patterns. So this is quite closely related, I think, mathematically to solitary structures. But these are extended patterns. So this goes back to the early 50s. Alan Turing is now more famous in, at least in the popular sphere for work on computing and the Turing machine, Turing test, things like that. But at the end of his life, he became very interested in biology and asked himself, where do these kinds of patterns come from? Things that are homogeneous can form into something which is not homogeneous, and this is very strange. So he introduced the very general form of an equation. This is called the reaction diffusion equation, which combines some kind of generally nonlinear reaction term with diffusion. So you want to know, well, Why does this appear? Okay. So what Turing figured out was that originally studying a two species system, but these are in one species, three species, on and on, and you get interesting behavior. What Turing showed is that if you pick in general some reaction F and some reaction G, so that there is some stable homogeneous solution, right? When you just have the nonlinearities, you have no diffusion. So assuming everything is homogeneous. And then you add back diffusion. The linear stability analysis shows that adding diffusion actually leads to instability in some cases. So this is very strange. It's not as strange now, but at the time, there was quite a lot of debate about whether or not this broke the second law of thermodynamics, because diffusion wants to spread things. And here we have diffusion actually doing the opposite and actually causing patterns to emerge. And this is very strange. Actually, several years before Turing's paper in 52, that was solved. And later Zagatinsky tried to publish their experimental work showing exactly this kind of reaction in chemistry. And it did not make it through peer review for several years and actually never made it through peer review. They just self-published it at some point because no one thought that this could happen. So Turing's mathematical analysis showed that. Okay, so this is old mathematics, right? But there's actually been quite a lot of activity, especially in the sphere of curved spaces, if you will. And this is because it's not always a flat space which we're interested in, right? We have this guy you can actually see as body curves. There's actually a change in the kind of patterns that are supported. Okay. So how does diffusion actually arise in nature? These are classical systems I've been talking about. You can think about things like the Drude model of electronic transport, Brownian in motion, right? These are many objects which move chaotically. In the case of Brownian in motion, this is many small particles giving a random push to some larger particle, which causes diffusive transport. Even in quantum mechanics, we have things like Anderson localization, which all involve some form of disorder. So again, we have a microscopic picture of disordered dynamics, right? But what we see is something like this, right? You have a concentration of something, it's going to homogenize. Okay. And this is easy math, right? This can be worked out by having some popping probability in a random walk, right? Saying that at small times, some particle gets a random hit in one position or the other position, and then maybe it's this position and maybe it's this position. And what happens in the continuum picture as we expand is that you generally get some kind of a diffusion, a convection diffusion equation, right? So if there's the same probability of popping in either direction, then the convection term goes away. But in general, this is what we get. So some diffusion in some drift velocity. Okay, so this is the classical picture. What does this have to do with quantum models that I promised in the title? Now, in terms of mathematics, the relationship between quantum mechanics and classical statistical physics is really quite simple, right? The fundamental equation of the quantum mechanics, even for a single particle, not a many body system, is a Schrodinger equation. Yeah. And if you take a so-called quick rotation, this is taking time to be imaginary, then we get changing the names of variables, reaction diffusion, right? Where the reaction term is simply a rescaling of whatever the single particle potential was. So there's a line in Z's quantum field theory text, I think is nice. Noting that this relationship between quantum and statistical physics is really quite interesting, and that we maybe don't understand it very well. I'm not going to try to answer any profound questions here. I'm going to answer something a little bit less profound, which is just to ask, can we do this physically? So something where we take a purely quantum system and turn it to what is generally very classical, right? A reaction diffusion equation that happens on biological scales. Okay. To do that, we have to go to something called non-Hermitian quantum mechanics. So in the 90s, Carl Bender and his then student, I think my postdoc, Stefan Becher, showed that while it had been generally assumed that Hamiltonian would have to be Hermitian for it to have a real spectrum, this is not always the case, that there are some class of non-Hermitian Hamiltonians which actually give you a real and therefore physical observable spectrum. And you can see spectrum here takes of a Hamiltonian, which is very much not Hermitian, that's an imaginary term, but which can actually, for certain n have perfectly real spectrum non-trivial. Physical observer. Okay, and this has actually been, it's gone from theory lands to some very practical applications very quickly, most notably in optics. Things like unidirectional invisibility, negative refractive indices, sensing that gets enhanced near the point where spectra go from real to complex, known as the exceptional point. And then also edge effects. And this is really what I want to highlight. One thing in particular that's been noticed is that in non-Hermitian systems, there's something which has been dubbed the non-Hermitian skin effect, where there is some tendency in non-Hermitian systems to have exponential localization of the wave function density near some boundary. So, turning time imaginary is not very visible. Okay. So this is again the Wick rotation. Time becomes imaginary, and we go from a Schrodinger to a reaction diffusion equation. Okay. But let's propose something slightly different. What happens if instead we leave time and we have a mass that somehow gets an imaginary character? Mass becomes imaginary, then our rescaling of variables is slightly changed, but we still get from a Schrodinger equation, very quantum, to a very classical reaction diffusion equation. So essentially, I have an asterisk on same, the constants are different, but imaginary mass would lead to the same thing as an actual Wick rotation having imaginary.
But you heard me mention that in R.
D, that's coefficient, that's imaginary.
What was that?
Your D,
No, imaginary R, right?
Yeah,
So the potential.
yeah, the
Yeah,
potential
like-
would also be imaginary, yeah. Yes. Okay. So this brings us to something called the Hatano-Nelson model. Okay, so this is a classic model, it's a type binding model. Okay, so we have some lattice, and we assume that the quantum particles are well localized at each one, and they are transported via tunneling. Okay, In this case, you can have some kind of a popping amplitude or tunneling amplitude from one side to the next. And these can be realized with asymmetric tunneling amplitude, so it can be more likely to tunnel to the right than to the left. And this happens in certain kinds of atomic chains. So this gives us a Hamiltonian that looks like this. When we take a continuum limit, we get something like this, which is has kinetic energy term, some kind of other asymmetric term here. Okay, because these are quantum objects and we're not necessarily in the Hermitian space, right? We can take these tunnelings to be generally complex. So this is something that can be done in the laboratory in these kinds of systems. So if we take the rightward tunneling, the leftward tunneling strength to be imaginary, but equal, then this term cancels, and we are left with a reaction diffusion equation. So, as was observed before, B would also have to have been imaginary. But this is realized through gain and loss in the physical system. So this is far beyond the exceptional point in the non-Hermitian language. So this already is some kind of reaction diffusion equation emerging directly from a non-Hermitian quantum chain. So this has a well-known solution. Of course, it depends on the boundary conditions. In this case, 0 on the boundaries, and this has a nice solution. Let's say that we don't have balancing rightward and leftward drift, or tunneling, then you're going to have some kind of finite drift, right? Some convection on appearing as well. So this is some, if this is constant along the lattice, the tunneling amplitudes, then that convection is going to be some constant term, depending on the ratio of rightward and leftward popping. Now, there's an interesting way to interpret this kind of,
Is U complex or real?
here U is real.
So in order for you to real number.
This cancel would be, there's an I and cancel would be I here. Okay, so there's another way to interpret this convection. Okay, so we're going to ask if we can rewrite this a little bit. So say that we want to know if we can rewrite this in some other spatial variable where we only have a kinetic energy term. So only diffusion in some space. Okay. So we can define some other variable. We can expand, change a variable, expands, change a variable, and it gives us some kind of a simple condition under which we can define this kappa, and this depends only on our choice of z, and in this way, we can define this change of variables such that we can rewrite the convection diffusion equation that we applied that as simply a diffusion equation without convection in a space where this differential operator, the constant drift, is equivalent to the differential operator that you would have This is the Laplacian in hyperbolic space. But this is if you were to take the continuum limit of instead of a random walk on even space, the random walk on space like this, where you have multiple branches at each level. So this is called the Muttalib. And doing the same derivation of a random walk on this space, we would get exactly that. So, well, that's a very simple case where there's constant convection. This is very easy to generalize and helps explain some of the things that you see here. So again, understanding the connection between our convection diffusion equation and our diffusion equation in a hyperbolic space, this also lets us map our previous solution to the simple reaction diffusion equation to something in that hyperbolic space. And so we can get some exact solution, which is actually an example then of what I was talking about before, non-Hermitian skin effect, where we have exponential localization on the boundary. So this then becomes even though this is from a quantum system, this is a classical realization of the quantum non-Hermitian skin effect. So again, the drift term is quite interesting. So this group is very interested, I think, in shock formation. So the original model, which is the type binding model, assumes that we have very well localized wave functions at each lattice site. So if these lattices actually start to overlap, so say that the type binding model doesn't apply at all, then it's very difficult. As you know, this is a many body quantum problem, and that's not generally solvable. But somewhere in between type binding and many body, you end up with nonlinear dependence on tunneling amplitudes. And so what this comes out as is a tunneling which depends on population, and therefore in our reaction diffusion equation, this is a convection which depends on population. So this is potentially realizing something like Berger's equation or something like that. So we can extend this quite a bit, right? The same central arguments apply for different kinds of hopping, right? Different microscopic physics. So if you add not only the nearest neighbor hopping, but next nearest neighbor hopping as well, which again happens quite generically in these physical systems, then what comes out is something continuum Hamiltonian, where we have not only a second order differential, but a fourth order differential, depending on nearest neighbor hopping alpha and next nearest neighbor hopping beta. So if we choose these accordingly, then we can also get some kind of a subdiffusive, just fourth order term, cancel the regular diffusion. So this is quite nice. And then if you do the same thing, but we don't cancel regular diffusion, instead we add more terms. So on-site nonlinearity, again, this is generically realizable in physical systems. Then we can actually get something that is really very generic, right? This is suddenly the complex Swift-Hohenberg equation, right? Alpha and beta can be complex because our tunneling can be complex. And this really, from here, we can get any kind of non-equilibrium nonlinear pattern forming dynamics. So yeah, this is this is really from this. Most other like pattern forming models in biology fall. So we've made it to some take home points. Really what I want to get across is that these weird non-Hermitian quantum systems can actually be leveraged to realize very much non-quantum phenomena without having to rely on the averaging out of the quantum phenomenon. So usually when there's some road from very much quantum behavior to classical behavior, there has to be some kind of a thermalization, some kind of an averaging out of all of the quantum behavior to get there. And here that's not the case. We can directly have complex tunneling in very controllable atomic chains. This could be in cold atoms. This I'm told that they can realize this in superconducting circuits. Where simply by changing the phase of your tunnelings, you can realize very much behavior very much associated with classical systems. The other point is that whether or not it's simulated in a quantum system, any kind of convection in a reaction diffusion equation is equivalent to having no convection in some curved space. Here I've only discussed the simplest case where constant convection maps to hyperbolic diffusion in the hyperbolic space, but this is easily generalized to some other interesting spaces as well. And then the last thing is just that classical and quantum transport are not as different as maybe it's. Yeah, that's it.
Thank you, Sam. Do we have any question for Sam?
Yeah.
So it's document for what you are describing. It's something that's very close to some things I studied when I was working on mean field game theory. So essentially, what you are dealing with is complex time nonlinear equation. And you can, even if you are non-Hermitian, you can bring lots of methods from quantum mechanics to study this kind of systems like WKD, of course. But one thing that's important in our case is that the functional space of solutions is very different than the one from Polynomial, because your fields are complex, they are positive definite. Is this something that you need to consider here?
Yes, so this is an interesting point. So if, for example, so the wave function psi is still going to be complex, right? So here that's fine because in complex Muttalib-Borodin, that is also the case. In a general reaction, in a purely real looking reaction diffusion equation with a complex variable, there's going to be no coupling between the real and imaginary particular wave function. So there's a sense in which you can treat this as too real.
So yeah, in the end, that's what we have two real equations. So the point that you use with these structures, and maybe it's related to this comment I noted. There's the fact that there are not complex conjugates. It's things that's more relevant.
Let's talk to you about that.
Why there are three vertical lines there in nonlinear term?
There's a problem.
Simple.
Yes, right.
So you mentioned that this model or simplified version, if I understand correctly, could be realized in experiments. So in a cold atom or superconducting circuit. So if you go back to the equation with U and D, and you said that for large U over D, you got the skin effect. Can you map this model to the actual experiment? And how big can they achieve U over D?
So no one has yet done this like transformation. My experimental friends say that they can, and I've no idea. Those things are slow, but as far as how much U over D can be, this is very tunable. In that U can be as high as the difference in tunneling between left and right is, and microscopically, usually this is some kind of a A B chain, right? Where A can go to B, but B is slower going to A. I think the first model of that was polyacetylene or something. But they can make those very, very different, A to B and B to A. So then whatever D is, U over D can be quite large.
Okay, I have actually a question, maybe more naive question. Because when you do this Wick rotation, so you obtain the reaction diffusion equation, but can you infer something from the reaction diffusion to the initial, I mean, quantum? I'm thinking it's a little bit linked to what Thibault was saying, but if you take so Schrödinger with potential, but you had a nonlinearity. So I mean, this kind of Gross-Pitayevsky for BEC, for instance. If I remember well, when you do this Wick rotation and you evolve in time, you will find the lowest energy state of your Gross-Pitayevsky equation, or you will find some kind of stationary solution. I mean, can you infer something more than just this? I mean, evolution towards the equilibrium from the reaction diffusion, or is there?
So it's important to note that to get this transformation, really the quantum thing that's happening is
in the potential,
which is imaginary.
Yeah.
Right. And so an imaginary potential, physically, this is having some kind of this is very far from equilibrium. This is non-conservative. This is gain of wave function, loss of wave function. So there's not in general going to be a tendency towards.
Okay, so it's very, very different from the Wick. But you can still, I mean, somehow infer something from the original.
It's still a quantum problem.
Mm-hmm.
It doesn't appear that way. This is really where the interesting thing lies. When you have non-conservative quantum mechanics or non-Hermitian quantum mechanics, as it's called, then the behaviors become very different, and it's we're still trying to understand how different the rules look like. And so what this shows is that some of the emergent phenomena that comes from non-Hermitian quantum mechanics, this is quite simple, right? This is a fairly mundane thing in the laboratory, right? You can imagine in a wave tank, well, you're just going to pump more waves, right? This imaginary potential term. But this is happening on the quantum scale. What emerges from that is quite strange if you're used to quantum behaviors in the equilibrium, so the conservative. This is where we get the quantum conversation.
Okay. Any other question for Sam? If not, let's thanks our speaker again. So tomorrow, same time at 3 p.m. Roberto Canassa.
Stop is that tomorrow?